welcome back everyone. In the last week, if you recall, we had been talking about chemical reactors, the design principle of that, and this week we are going to continue with the same topic and in the same vein. So, a little bit of recollection of where you were left in the at the end of the last week. So, we had talked about different kinds of reactors. Say you have batch reactor or CSTR, continuous start tank reactor, or plugged flow reactor, or for example PBR, packed bed reactor. Now, if you are looking at, for example, the mole balance of these reactors, so correspondingly I am going to write down again dNj dt equal to Rjv. Then for CSTR it is V equals to Fj0 minus Fj divided by minus Rj. So, this is molar flow rate in, molar flow rate out. This is the rate of the reaction for the particular species, jth species. For PFR it was dFj dV equals Rj, and for PBR it was dFj dW equals to Rj prime, W being the catalyst weight. And then also we expressed this mole balance in terms of conversion, in terms of we had expressed this. It was required because when we are trying to target a particular conversion for a reaction, what we need to know is with respect to that targeted conversion, how the different parameters have to be adjusted for that particular reactor, and the design equation gives us that handle once we are able to incorporate the conversion into this design equation. And what we had obtained then was something like this. For batch reactor it was T equals you integrate from 0 to x a, where x a is the targeted conversion, N a 0 divided by minus R a into dx a by V. For CSTR it was volume equal to F a 0, F a 0 being the molar flow rate in for the component A, F a 0 into x a divided by minus R a. For PFR it was V equals to integral 0 to x a minus F a 0 by R a into dx a, and for PBR the weight of the catalyst is related to conversion 0 to x a minus F a 0 by R a prime into dx a. And when we derived these expressions, we started from the expression of rate. So, the rate as a function of the concentration of different species, and then we expressed the concentrations of different species in terms of the conversion, the so called stoichiometric table, and then we combine these two, the rate law and stoichiometric table, in order to get a final expression of the rate in terms of the conversion for the reaction. And since the rate appears in all the design equations, then you replace the rate with that particular expression and you get your final expressions. We discussed these things in detail in the last week. Now, if you can recall also, we specifically talked about this, say batch CSTR reactors, PFR reactors, some problems we are going to also discuss this week. But say for example, if you are looking for CSTR design equation here, so if you are targeting a particular conversion, what is the volume that is required? We told that we have to do what we call as Levenspiel plot, where you plot F a 0 by minus R a, this term, as a function of x a, and then you are targeting a particular conversion, let us say x target. So, the volume of CSTR necessary is the area of the corresponding parallelogram. So, this length into this length. So, basically then the volume necessary will be F a 0 by minus R a at x equal to x target x equal to x target into x target. These things we discussed. We also told that when we go to the PFR, we have to actually solve this integral, and for that we have a numerical approach to approximate the expressions of these integrals, like Simpson's 3/8 rule, Simpson's 1/3 rule, trapezoid rule. We did some problems, and also we told that basically if you are targeting the same conversion in CSTR as well as PFR, then the CSTR volume necessary is this volume of this parallelogram, and the volume of the PFR necessary is basically the area under this curve. So, the volume of PFR necessary will be less. Also we talked about a targeted conversion. If we are trying to achieve by using 2 CSTRs in series, then the total volume necessary will be lower than the volume necessary if you are using only one CSTR to achieve this particular conversion. However, if you are using PFRs, if you are using several PFRs in series, or if you are using only one PFR and targeting a particular conversion, the total volume necessary will be the same. It is always the area under the curve. These things we discussed, and we also worked out some problems. So, today we are going to start with the topic of selectivity. So, very quickly we are going to discuss how the selectivity governs, selectivity of a chemical reaction governs whether to use one kind of reactor or another kind of reactor. Say for example, if you are comparing between a CSTR and PFR, the continuous start tank reactor and a plugged flow reactor, which one to use and why. So, let us say you have a reaction, generically this is A is the starting material, and A can give rise to a desired product, this is the desired product, or A can give rise to an undesired product, undesired product. Let us say the rate constants for them is correspondingly small k d, and here it is small k u, d being the suffix to tell you that this is the rate constant for desired product, this is the rate constant for undesired product. So, what is the selectivity? Let us just say selectivity S, selectivity of the product d over u is equal to rate of the formation of d divided by rate of the formation of u, and that will be equal to k d into C A to the power alpha 1 divided by k u into C A to the power alpha 2. I mean, let us say this follows a rate law where the rate is having an order alpha 1 with respect to A, then it will be rate constant into concentration of A to the power that term. So, correspondingly for the undesired product, let the rate expression be this. So, the order of the reaction is alpha 2. So, this will be then equal to k d divided by k u into C A to the power alpha 1 minus alpha 2. Now, there are two situations that you can envisage here. If alpha 1 is greater than alpha 2, it is possible. If alpha 1 is greater than alpha 2, then from this expression, as concentration of A goes up, the selectivity also goes up. This is what you want. So, the question is, in this situation, whether you are going to use a plugged flow reactor or CSTR, which one is going to give you better selectivity? Intuitively you can understand this, that this expression tells you if the concentration goes up, then the selectivity goes up. Assuming this alpha 1 is greater than alpha 2, then this is valid. So, if you are looking at a PFR, then the concentration progressively changes as you go along the length of the tube. We talked about it is a cylindrical tube, there is a concentration gradient, although radially means along this direction the concentration does not change, but the concentration progressively changes along this direction. You start with a higher concentration and you go to a lower concentration, say you are talking about a reactant, say A. So, there is a concentration gradient. So, situations where higher concentration are there are also encountered here in this reactor, because it starts from a higher concentration and goes to a lower concentration. On the other hand, if you are looking at CSTR, basically you are putting say a higher concentration of the reactant you are putting in the feed stream, in the inlet stream. When it goes in the reaction mixture, it immediately goes to the diluted condition, because the reaction mixture is operating at a steady state at a particular conversion. So, if it is operating at a particular conversion, then the concentration of all the species present, including reactant as well as the product, all of them are constant whatever it is in that reaction mixture. Say you are actually opting for 80% or 90% conversion, then generally or naturally your concentration of starting material is quite low in that reaction mixture, because it is always operating at that particular conversion. So, whatever higher concentration you start with in the feed stream, when it goes in, it immediately gets diluted to that steady state concentration of your starting material, which is lower, and that concentration does not change with time. So, you do not encounter this kind of thing where you can go from higher concentration to lower concentration. That higher concentration regime you do not access in CSTR. So, the selectivity will be lower for CSTR. This is what you can understand intuitively. We will come to it graphically after. Now, let us say we are talking about alpha 1 less than alpha 2, another case. So, if this is the situation, say alpha 1 is less than alpha 2, then as the concentration of A goes up, selectivity goes down. In that situation, you will basically use CSTR, where your reactant is in diluted condition. You are doing the reaction at a lower concentration of your starting material, because the reaction is already in progress and in steady state. So, conversion does not change, the targeted conversion whatever you are looking for, and concentration of reactant or whatever, they are diluted species, because that has been diluted into the reaction mixture after coming through the feed stream at a higher concentration. So, that is the concentration at steady state does not change. So, this is a lower concentration than the concentrations that are encountered in PFR, at least in the regime, in the region where the entry point is there. It enters with a higher concentration and slowly and gradually it goes down as you go along the length of the tube. So, if alpha 1 is less than alpha 2, you will get a better selectivity in CSTR than PFR, and if alpha 1 is greater than alpha 2, then you will choose PFR. So, in this case you will choose PFR, and in this case you will choose CSTR. Now, I mean, we are talking about this selectivity. It is also important to talk about overall fractional yield with respect to this selectivity. So, overall fractional yield, let us say this capital phi, it will be equal to all of the D produced divided by all of A reacted. That will be the, that will tell you the selectivity. Now, if you are considering this case alpha 1 greater than alpha 2, let us now plot a graph and see the situation. So, you are plotting your yield with respect to concentration. Now, remember, if you are trying to get an expression for this yield of the desired product or the selectivity correspondingly, you have expressions like this. Say, if you are going for a CSTR, then this overall yield of this product, the selectivity for the product, this yield is basically equal to the yield at the exit and the and at a corresponding concentration of Ca. I mean, this is because whatever is the composition of the reaction mixture, that is the same composition that you are getting in the whatever is the output. So, whatever yield is there for D or the selective yield is there for D, the desired product, it is the same everywhere through the reaction mixture as well as at the exit, and this Ca is the concentration, steady state concentration of the reactant in the reaction mixture. So, that is why this phi CSTR is this. What about PFR? For PFR, the phi PFR is basically equal to 1 by delta Ca integral Ca0 to Caf phi dCa. This is because the concentration, there is a concentration gradient throughout PFR. So, you start from a initial concentration, you go to a final concentration. So, you integrate your yield over this whole concentration and then you divide by this change in concentration. That is something that is not happening in CSTR, because the concentration is always the same, yield is always the same everywhere. Here the yield is changing with respect to the length of the PFR. So, the overall selective yield for D is this. Now, let us go to the graph and let us consider the situation where alpha 1 is greater than alpha 2. Remember, when alpha 1 was greater than alpha 2, intuitively we told that we should use PFR, then we will get a better selectivity, and we do not use CSTR. So, let us say if alpha 1 is greater than alpha 2, then the curve will be something like this. It will be having a positive slope. You look at this, your alpha 1 is greater than alpha 2. So, your yield with respect to your concentration, that will have a positive slope. So, if your yield with respect to concentration is having a positive slope, it will give this kind of graph. Now, let us say this is CS0 initial concentration and this is final concentration. Okay. Now, what is the yield at final concentration? That is this value. Now, as far as CSTR is concerned, this yield does not change throughout the system. So, whether you are looking at this point or this point, your yield will be given by this particular graph here. So, you see here this area under the curve will be equal to your phi CSTR into delta CA. Now, if you are looking at this particular graph, so the yield varies like this with concentration. Okay. Yield varies like this with concentration. Now, when you are looking for CSTR, for CSTR this is the yield, and if you are drawing a parallelogram like this, the length of this side is basically delta CA, the change in concentration, and the height is basically the yield in CSTR. So, the area of this parallelogram will be giving you delta CA into phi CSTR. So, this is the area of the parallelogram. Now, what happens if you are looking at say PFR, the same graph if you are considering for PFR, then what is the situation? In PFR, so you look at this particular integral here. If you look at this particular integral, your delta CA into PFR is basically this integral, overall integral. So, that means, let me take a different marker. If you look at this overall area under the curve, this full area under the curve, what is this area? This area is nothing but phi PFR into delta CA, that is the area, because phi PFR into delta CA is the integral from CA0 to CAF phi dCA. This is nothing but the area under this curve. This area is basically bigger than the area that we had for CSTR, and for both the areas one term is common, this delta CA. So, from this graph also we can see that the phi PFR is basically phi CSTR, phi PFR is basically greater than phi CSTR, excuse me. So, phi PFR is greater than phi CSTR when alpha 1 is greater than alpha 2. So, graphically we can show that this is the case, also intuitively we understood. Now, what happens if alpha 1 is less than alpha 2? Then as a function of concentration, your selective yield will be something like this. Say here you have CA0 and here you have CAF. Now, if you are looking for this particular term which is phi PFR into delta CA, because this is the term that gives you this integral for PFR, and let us apply this situation for PFR, then what is this term? This is again the same, this is the integral under this particular graph, this curve, this is the whole area under the curve, this area is phi PFR into delta Ca. And what is the situation for CSTR? For CSTR, the area under this parallelogram is equal to phi CSTR into delta Ca. So, remember, when you are looking for the phi for PFR, it is basically an integration, because over the length of the PFR the concentration is changing. So, it is an integration. So, you see the integration here, whereas for CSTR you have only one phi, and that is this phi. This is the phi CSTR here, this is the phi CSTR, and that is why the area under the graph basically is your phi CSTR into delta Ca. So, that means this length into this length, that is the area under the graph. And for PFR, your phi PFR into delta Ca is basically the area under this curve. Again you see that the area that we are considering for CSTR is greater than the area that we are considering for PFR, and in both the cases one term is common, delta Ca, which is the same. So, basically here your phi CSTR is greater than phi PFR. So, when alpha 1 is less than alpha 2, your phi CSTR is greater than phi PFR. So, we showed both graphically as well as through intuition and through the mathematical expression here that when your alpha 1 is greater than alpha 2, you will get better selectivity when you are using a PFR, and when your alpha 1 is less than alpha 2, you will get a better selectivity when you are using a CSTR. Now, as we have completed our discussion on CSTR, let us go ahead and solve some simple problems again related to our chemical reactor design principles. So, let us define the problem like this. Say we are considering this particular reaction, and this reaction is first order in A, which means your rate law is this minus R A equals to rate constant into C A. Now, the question is you have to calculate the time, required for a conversion. Let us say we are targeting a particular conversion which is X A in a batch reactor, in a batch reactor of constant volume V equal to V naught. This is the problem. So, we have been given this reaction, this is the rate law. So, the question is what is the time required for a specific conversion in this batch reactor of volume V equals to V naught. So, when you are solving all these problems, you should go step by step, as we have discussed previously. You start by having the rate law expression. Here the rate law expression is given. Now, you start by writing down the rate law expression, and then you go to stoichiometry, that means the concentration as a function of conversion, and then you put them together in the design equation, you replace this R A. So, we will do that step by step. So, this is the rate law. So, the solution. So, rate law is already given. Now, what is the stoichiometric table that tells you? So, what is the stoichiometry? Remember, we constructed a stoichiometric table for batch reactor before in a previous class. So, that tells you your concentration of A at a particular time t is equals to initial concentration of A into 1 minus X A, where X A is the conversion that has been attained by the reaction at that time. So, this is C A equals to C A 0 into 1 minus X. Then once you have elucidated the rate law, and then once you have constructed the stoichiometric table or expression, then you directly go to the mole balance or the design equation. So, the mole balance is basically nothing but dNA dt equals to RAV, if you can recall from a previous class. This is the mole balance. Now, remember that Na, that is the number of moles of A at a particular time t, is equals to initial number of moles into 1 minus x. So, if you replace that here, then what do you get? ddt of Na0 minus ddt of Na0 into x or xa. Now, ddt of Na0 is 0 because Na0 is constant, and ddt of Na0 into minus xa will be equal to, so the minus term will come out, minus Na0 ddt of xa, and rate you are putting this expression k into Ca, that you can put here, minus k into Ca into V. The minus goes, so that will be Na0 into ddt of xa equal to minus k, so minus is not there anymore. So, k into Ca, Ca you can get the expression of Ca in terms of conversion and the initial concentration. So, just put that expression here, k into Ca0 into 1 minus x. And V is V0 here, V0 is basically the volume of the batch reactor, we have already defined the problem before, and this is basically xa. Now, V0, what is V0? What is V0? V0 is basically nothing but, so like this, Na0 divided by V0 is equals to Ca0. So, concentration is equals to number of moles divided by the total volume. So, V0 is nothing but Na0 divided by Ca0, right. So, V0 will be Na0 divided by Ca0, the Ca0 goes and Na0 also gets cancelled out. So, ultimately we are left with solving a simple integral. So, dxa divided by 1 minus xa equals to k dt. So, you integrate from time 0 to t, this time t, that is the t is what the time is that you are trying to find out with respect to the particular targeted conversion, and then this is also integrated from 0 conversion to the final conversion. So, if you do this, you will get the final expression as 1 by k into ln 1 by 1 minus xa equals to t. So, this is the final expression. This expression tells you that if you are targeting a conversion which is xa for a reaction like this, where the reaction is first order in A, then this is the time that is required, and k is the rate constant for this reaction. So, like this you can solve different problems. Here I did not give you any particular values for the different species, the amounts of different species, I just gave you a general term. Now, if the rate is second order in A, then accordingly this integration will change like that. So, this is the general thing. Now, if the rate is second order, you can change the Ca accordingly, it will be Ca square, then this will be Ca0 square into 1 minus x square, and then the integral will change, and ultimately the expression will also change, but overall this is the principle. Okay. So, now before closing this class, we will do one more problem. This time let us do a problem for CSTR. Okay. So, let us say this is the reaction we are considering. This is a liquid phase reaction which is having an elementary rate law, and as you know, elementary rate law means it will be k into Ca square, because this is the coefficient and that will be exactly equal to the concentration to the power whatever is the order of the reaction with respect to that species, that will be equal to the coefficient which appears with that species in the reaction. So, this is the elementary rate law. Okay. It could be Ca to the power cube, or it could be Ca to the power 0, or it could be Ca to the power 1, then it will not be elementary rate law, or Ca to the power 0.5. Okay. So, elementary rate law. Now, you are doing this reaction in a CSTR under isothermal condition, that means the temperature is not changing. You can take away the heat if it is exothermic reaction, so on and so forth, you keep the same temperature throughout. Now, pure A is entering the reactor at a volumetric flow rate. So, small v is the volumetric flow rate in at a volumetric flow rate of 25 decimeter cube per second, and the concentration of A that is entering, that means Ca0 is equal to 2 moles per decimeter cube. Question is, what is the volume of CSTR necessary in order to achieve a conversion of 90%? So, we know the volumetric flow rate, the flow rate at which it is entering. We also know the initial concentration at which it is entering, that is the feed concentration, and we also know this is the rate expression. So, question is, can we find out the volume for which we can achieve 90% conversion? Something else is missing here, we need also a value of K, rate constant. It is also given 10 decimeter cube per mole second. So, that defines the whole problem. So, again your rate law is there. So, start by writing down the different expressions. So, you start with your rate law. Your rate law is minus R A equals to K into C A square. Then you go to stoichiometry. So, rate law, stoichiometry, mole balance, the same sequence we are following all through. Then you go to stoichiometry. For stoichiometry, your Fa0, that is the molar flow rate in, is equal to your concentration of the entering A into the volumetric flow rate in, that is the thing, and your molar flow rate out is equals to volumetric flow rate out into exit concentration of A or the concentration of A in the reactor. Now, this volumetric flow rate out is equal to volumetric flow rate in when you are doing a liquid phase reaction and if the CSTR is operating in steady state condition. So, V equals to V you can replace by V naught. So, this is the situation then. Also, your CA, concentration of A, is nothing but Fa by V or V naught, the same thing, I just put it here like this, sorry, this is Fa, and Fa is nothing but Fa0 into 1 minus x. So, this is this divided by V0. Now, you can write down the mole balance. So, if you write down the mole balance, what do you get? You get V equals to Fa0 into x divided by minus Ra. This is the expression for V. Now, from these relationships, what you can write here? You can write V0 into Ca0, because Fa0 is basically V0 into Ca0 into x divided by minus Ra. Minus Ra is K into Ca square. So, that will be K into Ca square. Now, what is Ca square? This Ca has this expression. Now, Fa0 divided by V0, molar flow rate in divided by volumetric flow rate in, is nothing but the concentration at which it is entering the Ca. So, this ratio from this expression, this comes out to be Ca0 into 1 minus x. From stoichiometric table already we had elucidated this before. So, minus Ra equals to K into Ca square. So, that will be Ca0 square into 1 minus x whole square, right. So, from here what you get is this V equals to small v0 into x divided by small k into Ca0 into 1 minus x. So, targeted conversion you know, volumetric flow rate in, everything you know. So, volumetric flow rate in is 25 decimeter cube per second, x has no unit, 90% conversion, so into 0.9. So, you put it in fractional terms. Now, small k is 10 decimeter cube per mole second. Now, entering concentration of A is 0.2 mole per decimeter cube into 1 minus 0.9 square. So, always write down the units, so that ultimately you will see that you will get the unit of decimeter cube, the moles second, these things will go. So, the ultimate expression of V from here, as I have calculated already, is 1125 decimeter cube. This is the volume you require to get that particular conversion. Furthermore, I can ask you, what is the residence time? What is the residence time for this problem. So, if you have 90% conversion, you find out the volume, then what is the residence time that you get. So, what is residence time? Residence time is how long the reactants or whatever species is there, they stay in the reaction vessel. So, the residence time is nothing but capital V divided by small v. Capital V is the reactor volume divided by small v, which is the volumetric flow rate in. This ratio is your residence time. Okay. So, this is your residence time. So, in this case the expression, so this what does it tell you, what is the residence time? Capital V is already known and small v is already known, 25 decimeter cube per second. So, if you take the ratio, it will be 45 seconds. Now, this residence time is very, very important. You can change the residence time by changing the volumetric flow rate in. When the capital V is constant, you are not changing the reactor volume, but you can change the residence time, and if you change the residence time, you may change the extent of conversion. Okay. So, we will stop here today, and we will continue to discuss different problems and progress in terms of also understanding some other remaining concepts for the chemical reactors. Till then, goodbye and see you in the next class.